Fantastic. So we've spoken about verification and validation, and I'm just going to remind again the importance of verification and validation. So verification, really the important aspect about making sure that we have computed the right mathematics. So that is critical. And validation is really making sure that we are modeling appropriately. So with what we want to represent mathematically, making sure that we represent that appropriately. Okay, so validation is an essential outcome for a research project in your fourth year. So that's critical. And what I would like to just expose you to is just one of the oldest techniques for validation of FEM. In terms of, it allows you to have full field stress estimates, and that's called photoelasticity or photostress. So there are a couple of names for that. So what I would like you to do is please watch these 3 videos before you continue. That is important. Okay, so that you have a good understanding of more or less what it's about. And then once you've watched those 3 videos, you can maybe unpause this one and then continue watching. Maybe some of the things that I'm going to show you now might not make sense if you haven't watched those 3 videos. I've tried to select the shortest videos I could find on YouTube that explain this. I wanted to actually make my own videos, but with the access to campus and with colleagues not being on campus, it's the photoelasticity box is an issue at the moment to get hold of. So we have a box of photoelasticity stuff that has samples that I'm going to show you later on here. So I'm not going to be able to show you the samples themselves, but you're going to see pictures like this from that photoelasticity box. And unfortunately, I can't demonstrate that with my own videos, but these videos will give you absolutely an idea of what's going on. It will give you a good sense, maybe much better than what I would have been able to do, because some of them are from companies. So please, I'm not trying to endorse any companies here or anything like that. This is just to make you aware of the content. So forget about the companies that are behind those videos. That's not the aim of the videos. Okay. So first off, photoelasticity. Consider essentially for plane stress measurements. Our third principal stress is 0. So that's the out of plane stress component. So principal stresses are essentially all in play. So we can, with photoelasticity, determine 2 things: isoclinics, which is not what the focus is going to be for this validation notebook, but I just want to make you aware of it, that you just because you'll often read this or bump into this in literature, that you just understand at least what's the context behind it. So isoclinics are essentially black and white fringe lines where each black line really represents points with the same principal stress direction. Okay, so that's really what it implies. And if you recall from your second year MOW227, you had those transformation equations from going from one for your one coordinate system for your stress description, let's say the Cartesian XY, to another coordinate description that's given rated by an angle theta with respect to your XY Cartesian coordinate system. We could essentially say, well, okay, let's look at for a specific principal stress orientation. I would like to know, which points are stress orientation aligned with this sigma p principal stress orientation. Apologies. To determine that, all that we need to do is we need to say, well, essentially, what it boils down to is the fact that the transformed shear stress must be 0. So that's really what that boils down. So I can really plug that in there, and then I can give a description saying if I choose a principal stress direction, essentially all stresses with that have this relationship will be in that stress direction. Okay, so that's that principal stress direction. That's really what this isoclinics allows us to do. Isochromatics is really what this is going to be about. So all the isochromatics are the colorful pictures. So they also a little bit more, it's a little bit more, I think, making engineering a little bit more sexy in terms of seeing that we can actually have full field stress descriptions for structure under load. So isochromatics are the lines of constant colors. Essentially, when we have a white light source that we shine through the specimen, it's a bit of a setup involved. But you'll see one of the DIY videos will show you actually how you can do this yourself. So I would really encourage you to try and just take something at home and then actually try and model it in using the fun element package or this fun element code, just as a fun project for those of you that have capacity. But anyway, the colors are really related to the loadings. So each of these constant color lines that you see here are essentially just related to loading. You can see here there's parts of the structure that's not loaded. These black parts are parts of the structure that is not being loaded. Okay, but what it boils down to is it's really the loading of the. It's really just a constant principal stress differences. That's really the contours, what they relate to. Okay, so that's really what they are. The differences in the principal stresses that are constant. That's really what these profiles relate to. Okay, so each of these colors. And the relationship of that is just a material property, which is called the material fringe constant. It's related to the wavelengths and thickness of the material. There's essentially the fringe order, which is what is the number of the fringe. So if you start here, you see black, and we start getting a line here. So that's we start counting these lines, these constant bands, and we call each one an order. So they are these integer numbers, and then the thickness of the material. That's sort of the out-of-plane thickness that we are working with. That's really the relationship that's involved here. It's not important to memorize this at all. Just I want to show you, just to understand that it's related to the loading of the structure and specifically contours of principal stress differences. Okay. So that's each color line has the same principal stress difference. So each of those lines. Okay, so that's hopefully giving you a good idea of what that's about. Okay, so let's see how we can go about modeling this. So first off, we've got an input file, Polariscope 2. We get a magnification factor that I'm going to set to 1 using our LaunchFem program. Then we get some plots out. So let me open up this Polariscope 2 file first. You can just see more or less there is the nodal description for that. So these are just the nodes. So you can see quite a lot of nodes. So this is a program or model that has, and trust me, this was not done by hand. But so this is typically you would model this in. What happened now? Just want to get to the. Yeah, so we are close here. You can see there's a total of 10,940 nodes. These are the coordinates for those nodes, and then this makes up the mesh. So you can see what is the element type here. So that's even. So that's if you go back to your menu, it should be plain stress. And if you go 1, 2, 3, 4, 5, 6, 7, 8. So if you look at each of these elements, you see they've got 8 nodes. So these are Q8 elements, quadrilateral elements. So what I know is that these first 4 are related to the node numbering of the outside corners, and these last 4 are related to the mid-side nodes. Okay, so that's really what that boils down to. Now we can see how many elements we have. Boom, 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 go down, and we see essentially we have 3,487 elements to model this. Put in the value for the Young's modulus, put in the value for Poisson's ratio, the thickness, and here is essentially the boundary. So this is prescribed displacement. So prescribed displacement of nodes 6630 in the x and y direction is 0, 0. In the 3 direction, node 3 and node 10,917 in the y direction, this one is also got a 0 value, but this one's got a prescribed displacement that's non-zero. So first, maybe let's start modeling this thing as making it a 0, and I'm going to start making this value bigger and bigger, so sort of have an animation a little bit. And then there's just the loading, just has to have a loading, otherwise the file crashes, so this is just a 0 loading, so this is 0 traction, a concentrated load that we apply. That's what that was. So let's run this program quickly, make sure everything runs hunky-dory. What just happened now? Line of magic is missing. Okay, so there was now something awkward there. Now it's running. You can see the stars showing it's crunching on my machine. You can see 5 seconds assembly. There's some time spent doing all of this. Let's just wait for it. So I'm going to just run this one, and I'm going to stop the video because we're heading towards 10 minutes. And then I'm going to make another video after that. Ooh. Okay, so that it's not going to work if I just make it 0, so I'm going to make it some small value. It was 2. I'm going to make it 0.2. So just having no load, unfortunately, again, this is not a program that we're paying for. It's a free program developed, so it's not as robust as what we need. Commercial thing would be, but at least it's getting the idea across. So this is 0.2 prescribed displacement. Okay, so that's what we have. Deformed, undeformed, magnification. I think you can almost barely see what's going on there. And so this is this would be sort of a perspex cutout. That's typically how they would look. So you can think of this thing as perspex cutout. The 10,000 Young's modulus is actually double check if that's appropriate for perspex. Anyway, so the bottom line is, if I look at the von Mises stresses here, I see there's stresses are quite low, but it goes from 0 to 3. It should be MPa, and I'll tell you why I say MPa. So let's just go back to this. So this is prescribed displacement, so this is millimeters, thickness in millimeters. All of these coordinates, 57, 26, it's all millimeter descriptions that we've given here. And the Young's modulus is essentially given then in MPa. Okay, so you can ask yourself whether that is appropriate or not. So that's 10,000 MPa. Okay, so that, well, it just boils down to essentially 10 gigapascal. But that's what we have. Okay, so that's the first thing there. Then isochromatics. And again, the reason I highlight again what is this units here is we have to take care about the input file. There's no flag that we set to say this is the units of what the modeling is about. There's the isochromatic that we see. So there is essentially, you can see the black parts are not loaded, and then as you start going through these fringes, you can see that high loading. You can see lots of fringes rapidly in a short space, running over a lot of fringes there. And so what we see is there's some nice stress concentration that's happening. You can see here essentially the loading is quite relaxed, and then it gets, as we get to here, a lot more rapid. Okay, but you can see this is quite a high quality kind of image. It almost looks like a photo. And if I were to be able to compare this to the samples that we have on campus, you would not really see the difference. And so this is really telling us validation-wise. The theory that we've done, the finite element 1D stuff that we've done, and extending that basic theory to the 2D case, that's coming out of the simulation. It's really, really a complex stress field. So this is what we're able to actually model now from the theory that we've done in the course. And it's incredible. This feels like 2020 engineering, at least, as opposed to just prismatic kind of structures that we always load, uniaxial, uniform, or linear varying stress fields. Now we can see some nice complex spatial varying stress fields. And now you can also see the importance of making sure we develop capability to have stress fields that can be quite complex. As you can see here, this is a very complex stress field pattern that we see here. Okay, you can look at essentially the sigma xx. So that's the stress in the x direction. We can look at that. This is isochromatic now. This is just plotting a couple of these isochromatics. This is the same as that one. Then this is sigma yy. So that is essentially sigma in the yy direction, isochromatic, and then the sigma shears that you can see here. And you can see the shears are much lower than what you would see in the y direction. So you can see essentially compressive stresses in this side, and you can see essentially as you pull that thing towards its outside, you're starting to see some, and here as well you're seeing some tensile stresses forming there. And obviously the question maybe that you ask is this one going up or is this one going up? So we can ask ourselves, can we understand what's going on? If this is in compression, we expect that this one here at the bottom is moving up. What I want to do is now show you that by essentially making this 2 millimeters as opposed to 0.2, so we can actually visually see this loading that we're applying here. Let's run it again. That's one thing, we just put a value in there for 2 minutes, but we haven't asked is where is that applied and what's going on. So we'll now see the node that's moving visually. We'll be able to see that quite clearly. So there's the deformed, undeformed. You can see there that point now has moved up 2 millimeters. Beautiful. You can see that. And essentially we are compressing here. you've got forming some tension there, and then essentially some tension there because of that kind of 2 points moving closer to each other there. And again, now we can start looking again, seeing the von Mises stress going up to 30 MPa, start looking at the isochromatrics, and start getting an idea of what's happening here with the contours. And you can see now essentially this number of fringes would increase here. So as we go through this kind of process, you'll see the number of fringes increasing drastically. Sigma XX going up to 17 MPa, isochromatic, there's sigma YY 25. You can now see compressive loading here. Start seeing more of that sort of tensile loadings there, some tensile colors that's coming in there. And then the shears are also now up to about 8 MPa. And that's really what this allows us to do. So this is now full field validation, beautiful. It also is useful for calibration models. So especially when you have nonlinear materials later on in your careers, when you start making the postgrad FEM course, where you learn about nonlinear materials, so viscoelastics, plasticity, and those are things a lot more complex to calibrate. So elastic material is easy. It's essentially Poisson's ratio, or at least the isotropic ones are Poisson's ratio and Young's modulus. Poisson's ratio and Young's modulus, yeah. But then maybe composites, you require maybe a couple more coefficients to know, maybe the Young's modulus in different directions, Poisson's ratios in various directions. But that's just about as complex as what elasticity will go. It's really via orthotropic materials, etc. But when you get to nonlinear materials, this full field capability can be quite useful, especially as you've seen from one of the videos. You can get an idea at least where yielding occurs for this kind of, at least for the plastic, for these kind of plastic models. But this is really hopefully convincing you that what we've done in this course, all the 1D stuff that was so simple and basic, there's now value in seeing all of that is actually translated down to this kind of full complexity what we're seeing here.